Right, so using the bond enthalpy values to calculate another way of calculating enthalpy change of a particular reaction. Okay, so this is just another method of obtaining a calculated version of that same value that we've been calculating previously in the topic. So, as we saw on the PowerPoint a moment ago, just pull that down. In any chemical reaction, doesn't matter what the reaction is, doesn't matter what the reactants or what the products are, the same sort of processes are happening in terms of bond breaking and bond making. Because in any chemical reaction, some bonds are always broken and some bonds are always formed. And it requires energy to break bonds. Okay, bonds are formed because they are more stable than when they are not there. So in order to break bonds, it actually takes energy, it requires energy. You have to put energy in to break atoms apart and break the bonds between them. So bond breaking, doesn't matter what the atoms are or what the bond breaking is always an endothermic process. And so on the other hand, if a new bond is made, a new bond is formed, energy is given out, it's released. And so bond making is always an exothermic process. And I just like to remember that by putting that in the form of the way we would write a reaction. So if we've got reactants going to products, obviously that's any reaction, doesn't matter what. It's always the case that some bonds have to be broken on the left. Okay, these are the bonds, these are where the bonds are broken. Okay, so in the reactants, this is where the bonds have to be broken. So this is an endothermic part of the reaction. And the new bonds that are made are always the ones in the products. So this is always an exothermic part of the reaction. Now it's a bit strange to think that actually in a reaction we've got both endothermic and exothermic processes happening, but we have. But we already know that reactions are either exothermic or they're endothermic. We don't classify them as both. We would say that, if a reaction, when we look at it, if it gives out heat, then it's exothermic. And if it takes in heat, the temperature drops around it, then we would say it's endothermic. So now we're looking at this and saying that actually all reactions are actually both is a bit strange. And it's to do with the balance between these sides as to whether or not overall the reaction will be exothermic or endothermic. It's to do with how much energy is either taken in when this bit happens or given out when that bit happens. And basically if this side is bigger than the left-hand side, then it'll be exothermic. But if this side is bigger than the right-hand side, then it'll be endothermic. So it's all just dependent on that balance. So if the reaction is endothermic, overall, what this means is that more energy is absorbed when bonds are broken in the reactants than is released when bonds are formed in the products. So that's literally just putting into a bit more of a formal sentence what I just said. If the reaction is endothermic overall, it means what's going on the left-hand side is bigger, more significant than what's going on the right-hand side. So the other side of it then must be if the reaction is exothermic, this is exothermic overall, it means that the right-hand side is more significant, which means that more energy is released when bonds are formed in the products than was absorbed when the bonds were broken in the reactants. And so if this overall energy change is related to bonds being broken and bonds being made, we must be able to calculate it using bond enthalpy values. And we can. The energy change, delta H, for a reaction can be calculated using what we call average bond enthalpy data. So average bond enthalpy is a definition that you need to know and you need to remember. So here is the definition. It is the energy required to break 1 mole of a covalent bond in a gaseous molecule averaged over a range of compounds. So you saw that definition on the PowerPoint a moment ago, and there it is again, and you need to know it, you need to learn it. Okay, so remember that what that means is that it is the energy required to break 1 mole of a particular bond, but it's unlikely that that bond exists in isolation. So you wouldn't have just a carbon to hydrogen bond floating around on its own. It would be part of a bigger molecule that contains carbons and hydrogens. So what they have to do to work out the energy required to break a carbon to hydrogen bond is break those bonds in a molecule and then figure out what the carbon to hydrogen bond would be. And they don't just use 1 molecule, they use several different molecules and then take an average. Okay, so actually the bond energy of a carbon to hydrogen bond will be slightly different in different molecules. They will always vary slightly depending on the molecule they're in. So the value you get is an average. It's not a perfectly accurate number for every molecule. Okay, it's just an average. Okay, and as I said, those values for those different types of bonds can be found in the data book. Now, how to use them to do these sorts of calculations and work out an enthalpy change for a reaction is fairly straightforward. And again, we've got an important formula for you to remember. So to obtain that calculated value of delta H, here's your equation. So delta H, if we look up those bond enthalpy values, either in the data book or we could be given them in a question, then it's the bond enthalpies of the reactants minus the bond enthalpies of the products. So I quite like this one. It goes in the order that it happens in the reaction. So what happens on the left, subtract what happens in the right. Be careful here, because if you remember that other equation we had when we were using enthalpy of formation values, it was products minus reactants. Now it's reactants minus products. Okay, so it's the other way round to the enthalpy change of formation value method of working out delta H. Okay, so just one to watch out for. So if we think about an example, imagine we've got the complete combustion of propane. Okay, so propane is C3H8. I wouldn't expect you to necessarily remember that at the moment, but C3H8. Okay, if it's complete combustion, that means it forms carbon dioxide and water. So I've just balanced that out with the right numbers of carbon dioxides and waters to give us the right number of carbons and hydrogens, and then put the correct number of oxygens in to give us the right number for what we've got on the right hand side. Now, if we think about that reaction, we can think about it on one of those energy level diagrams. Here's the reactants, okay? This reaction is one which we know gives out energy, okay? It's an exothermic reaction overall, okay? It's burning a fuel, okay? It gives us energy. So here's the reactants, and the products must be lower down because we know it's an exothermic reaction. So energy is given out overall. But thinking about those steps and how we get there, before we get to that overall negative enthalpy change, we know it's going to be negative because we know it's exothermic, then the process that has to happen, theoretically, is that all the bonds in the reactants break, and that takes energy. So we go up to show bonds breaking. And once all those bonds are broken, then, well, what would we have? We would have 3 carbon atoms separate from each other. We would have 8 hydrogen atoms completely separate from each other. And we would have 10 altogether oxygen atoms, all completely separate from each other. That looks like 100, doesn't it? It's supposed to say 10 O. Okay, so 3C, 8H and 10 oxygen, to show that those atoms are now completely all separated from each other. And then once they're all separated from each other and the bonds are all broken, the new bonds can form and energy is given out. So bonds forming, represented by that down arrow. So endothermic, energy in, exothermic, energy out, and overall, more energy given out than taken in. So overall, it's an exothermic reaction. So that's the sort of principle behind what's going on. And all we're doing with this is we're putting in the values, and we're doing this, subtract this. So bonds breaking in the reactants, subtract bonds forming in the products to give us the difference. So in this one, we've been given the table of values, which is useful. If you haven't, you can look them up in the data book. So there we go. There's our values that we need and the bonds, types of bonds that we've got in these substances and their corresponding bond enthalpies. It's quite useful when you're doing this type of calculation to draw out the substances, draw out their Lewis structures, which you may know easily or you may have to work out. Okay, just a little bit close, isn't it? You can't quite see that. So we've got the propane, the 5 oxygens, the 3 carbon dioxides, and the 4 waters. So in order to work out the value, all the bonds in the reactants broken, added together, that's this what's in this first square bracket, subtract all the bonds that are made in the products, which is what's in the second square bracket. So if we look at it, look, we can see that there's 1, 2 carbon to carbon bonds. So we've done 2 times 347, which is the value for the carbon to carbon bond. Okay, and then it's 8 times 413. 413, look, is the value for carbon to hydrogen. Count them up: 1, 2, 3, 4, 5, 6, 7, 8. You do have to count carefully. This is why it's useful to have the molecules drawn out. And then obviously 5 lots of the oxygen to oxygen double bond. Don't be thinking that that's 2 bonds there. It's not, it's 1 double bond, and there's the value for that 1 double bond. Okay, so there are 5 of them, so 5 times 4, 9, 8. Okay, same deal for what's on the left, just with the carbon dioxides and the waters, and then you should end up with minus 1,700, if I've done my maths correctly, kilojoules per mole. Have a go, try it, and see if you get the same answer. Okay, and then if you stop the video and have a go at the ones on the next page, we will go through the answers in a moment.